So this short video presentation is going to show you how to put it all together. We've spent a lot of time looking at the different ways we can manipulate algebraic expressions. This one's going to show us how we can take what we learned about word problems and transferring them into algebraic expressions, and then use them to manipulate and simplify those expressions using factorization or binomial expansion or distributive law. So, like I said, it's using all those algebraic skills we have to convert between those equations and word problems. So this is a pretty important skill and allows us to manipulate real life, for want of a better word, equations. Allows us to model things. So here, we're going to do a couple examples. Here's the first one from your textbook. We have a rectangular swimming pool measuring 30 meters by 20 meters. A path around the edge of the pool is X meters wide on each side. So we've got a few questions that we're asked to solve using that information. And we're just going to work through them one at a time. So here's the first one, and the first part of our problem solving strategy is C. So for each of these parts we're going to go through see, plan, do, check. Now it's difficult for us to show that pro forma with these problems on the screen because it would get very small and cluttered, but we're going to talk about it as we go. So by seeing, what we're doing is looking for important information. So for this question, we'll start with the question, determine the area of the pool. So what information is going to help me solve that? 30 meters by 20 meters are the measurements of the pool. So it's just a rectangle. So our rule is area equals length times width. So that's our plan. Use that to solve the equation. So we substitute in 30 times 20, there's one of our algebraic skills. We get 600 square meters. So that's a fairly straightforward question. Part B says what happens when we add in the area of the path. So let's look at the extra information we have here. So our C is, go through here, X meters wide on each side. Now to make sure we get this right, it's probably a good idea to draw a diagram. So this is what it looks like. There's our pool in the middle, 20 meters by 30 meters. We work the area out to be 600 square meters. Now we add a path on the outside. It goes X meters on the top, X meters on the bottom, X to the right, X to the left. Now we're not quite sure what that measurement's going to be yet, and a lot will depend on what area we have to work with when building the pool. So the surveyor or the planner will consider that. So we have these considerations. The new length with the path is going to be the 30 meters plus this X, which is plus 2X. The width, adding X to the top, X to the bottom, plus the 20 of the pool. So that's 20 plus 2 lots of X as well. Going to the next screen, we've got those two measurements now, those two dimensions. Our rule for area is length times width. So we're going to substitute that in. So this bit here, substitute it for L. This bit here, substitute it for W. We get 30 plus 2x multiplied by 20 plus 2x. Now we should recognize that as a binomial expansion. So let's expand that out. 30 times 20 plus 30 times 2x plus the 2x here times the 20 plus the 2x times the 2x. Each term in the first bracket multiplied by each term in the second bracket. So that's 600 plus 60x plus 40x plus 4x squared. Group the middle term, the like term, plus 100x in the middle. So that's the answer to the second part of the question. Now, part C, this time what we're asked to find is an expression for the area of the path. So only the path. So for us to do that, we need to understand this. Area of the path is that total area we just worked out. Take the area of the pool, which we worked out in part A. So that's the expression we came up with for the area of the pool and the path in part B, and that's the expression or the answer for the area of the pool in part A. If we subtract them and take the difference, what we end up with is cancelling those 600, and the answer that's left should be the area of the path, 100x plus 4x squared. Now we're going to use that expression to answer the last part. If the path is 1.5 meters wide, calculate the area of the path. So when x equals 1.5, what we're going to do is substitute in. So wherever we see an x, we substitute 1.5. So 100 times 1.5. Remember, use bracket notation to make sure we don't get confused with our calculator. Plus 4 times 1.5 squared here. It gives you 159 square meters. Does that seem reasonable? Well, from the diagram, it looks like it's going to be a lot less than the area of the pool, which is 600. So it does seem reasonable. Let's just go back to that for a second. If our answer came to 700 square meters, it doesn't look like it's the area of the pool, so maybe we've made a mistake there. And part E, the last one here, if the path is 170 square meters, write an equation that could be solved. Okay, so this time we're going to use the same relationship we came up with. Area of the path equals that. This time, what we're looking for, sorry about this mistake, the area is 700 square meters. So A equals 7, sorry. The area of the pool path is 170 square meters. This number here. Same as we did before, we're going to substitute. This goes on the other side of the equation, the area of the path here. So it equals 170, and the expression equals that. We don't know how to solve that in grade 9, and that's something we explore further in grade 10, but that idea of substitution is pretty important. Now, if we just go back to part D, or even right back to this previous slide here, we had all the parts. This is a common sort of question from the textbook. What you need to consider though is to make an A-level question, we drop out all these other parts here. So only after part D you'll be asked that. Given this information, algebraically show, I'll calculate the area of the path is 1.5 meters wide, or something similar. So you've got to connect the dots in the middle. Alright, let's move on. So now I've answered that example. Second example is similar in design, so you may even want to have a go at it first. Once again, there's 5 parts. So let's break it down and look at the first part first. So here's our C part of our planning. Identify the critical information. The height and width, the margins on the top and bottom, and the left and right margins. Notice the different widths and different heights. Part A, what is an expression for the height of the page inside the margins? So let's start with a diagram, same as we did before with pool. There's the text inside the margins. There's the width of the entire page and the height of the entire page. We're talking about this. So if the margins are X centimeters at the top and the bottom, the height of the page has to be smaller. So we're subtracting 24 centimeters, take the X, take another X. It's 24, take 2X. We're going to use that shortly. Do the same thing with the width. This time the width is 16. We're going to take away those 2 parts. So we take 2y. And this is the challenge, of being able to pick out that information. And a diagram is really, really important at this point. So what's an expression for the area of the page inside the margins? So we know from the 2 equations already had, area is length times width. And this is our length and our width. So we substitute into the formula. And once again, same as in the first example, we're now using binomial expansion. So I've color-coded it. It's going to be 24 times 16, 24 times negative 2y, negative 2x times 16, and negative 2x times negative 2y. Looks like that. Looks like a lot of numbers. So 24 16 is 384. 24 times negative 2 is negative 48, and the y comes down. Negative 2 times 16 is negative 32. The x comes down. Negative 2 times negative 2 is positive 4, so it's plus 4x, y. So that's part C. Part D says, assuming that we double the left and right margins, what's the area going to be? So the margin is doubled. Instead of y on each side, it's now 2y on each side. So height doesn't change. It's still the same expression. But our width is now bigger. Instead of taking 1y, we're taking away 2y from each side. So we're actually taking 4y total. Interestingly enough, a good question to ask at this point is, what's the biggest margin we can have on the left and right? Let me think about that. If the margin was 4 on the left and right, we'd substitute in 4 for the y here. You get 16, take 4 times 4 equals 0. So if the margin was 4 centimeters, we'd have nowhere to write. So that's talking about reasonableness of a solution. So there's our area formula. We're going to substitute those two in again, like so. So we'll change it this time. Let's take the next page. Same as before. The only difference is that 4y. So it's going to affect the negative 2x times negative 4y and 24 times negative 4y. And we get this new expression with slightly bigger coefficients there and there. Now, what we want to do is work out how much bigger it is. So with the second page with the larger margins actually has the smallest area, so we're going to subtract it from the first. So the difference in area is our first expression we worked out minus the second. And there's a few things here that cancel out. They're common to both. Notice when I subtract, I put it all in brackets to remind me I've got to take away that each term as well as its sign, so I can match up signs more easily. So what that leaves me with is these things. Negative 48y, take negative 96. 4x, take 8xy. Let's take the next page. I've color-coded to make it easy to see. So negative 48 take negative 96 is positive 48. 4 take 8 is negative 4. So there's our expression, which is what we are asked to show. Finally, part E. If the margins at the top and bottom 1.5, left and right are 1, calculate the size of the area. So we can summarize that information there using our C. We've already worked out our original formula for the original margins. All we're doing is substituting in. Wherever you see a y, we put 1. If you see an x, we put 1.5. So there's x and y here. And we worked that out. 294 square centimeters is how much room we have for writing on that page. So these are some examples of some pretty tough questions. And as I said, to make them genuine A-level questions, we'd leave out part A, B, C, for example. What makes an A-level student or an A-level response is somebody who can connect the dots between the information given and the final part of the question. A good way to practice that is to cover up part A, B, and C. Can you answer part D? If not, then uncover part C, and so on.